All right, so three of our major players in translation are all made of RNA. They have different shapes, different functions, whatever. So tRNA has it's a folded single strand of messenger RNA, but it forms a T shape. It kind of looks like this. And then on the end it has some sort of amino acid. Okay, but three of the nucleotides are specifically designed or located in an area where they can bind with the messenger RNA. Okay, so the messenger RNA is just a single strand with a cap and a tail. And it has its own nucleotides with its own bases. And the anticodon, which are these three nitrogenous bases here, will bind with codons according to the base pairing rules. Okay, and what are the base pairing rules? How do the bases pair up? A with, well, now it's RNA, right? So we don't have T. A to U and G to C. Okay, so that's how the tRNA and the mRNA interact. The ribosomal RNA is also made of RNA folded up, and it has two subunits. So we have the small subunit and large subunit. And the messenger RNA then goes in between the two units. And then the tRNAs then go into three different sites on the ribosome: the A site, the P site, and the E site. So the anticodon and the codon are what bind, what determines what tRNAs are going to go and match up with the mRNAs. The ribosomes guide the process, and then they also form bonds between the amino acids. Right? So what's the bond that forms between amino acids? What's it called? Peptide. Good. And there's a specific part on the ribosome, I'm just going to say it's about right here, which forms the bond, and it's called peptidyl transferase.
What is it? I can't see it very well. What's explain it please to me?
I just drew a circle.
Okay.
Just a region in the ribosome which is responsible for forming the bond between the peptide, the amino acids. All right, so it does exactly what it says. It forms a peptide, and then it transfers the polypeptide to the tRNA at the A site. Okay? All right, so these are the different players, different structures that are important for translation. All right, what were the three phases of transcription? Do you remember? Initiation. So it starts with initiation. Elongation. Termination. Good. These are the same names for the same process, different processes, but the same names in translation. So we're going to start with initiation. All right, so we have our messenger RNA with its cap and its tail. And it has these bases here. And in order to start, the initiation sequence has to be recognized by a tRNA and the small subunit. And the initiation sequence is an AUG. Okay, so you may have a C, a G, an A. And the ribosome is going to just kind of read, the small subunit's going to read along there. It's not going to bind to anything until it comes to an AUG. Once it sees that AUG, then it will now bind in this area. Okay, similarly, you have your tRNA. And I'm running out of space here, but I'm going to draw it like this. And its anticodon is going to bind with that, so it's going to have a U, A, C, and it's going to form hydrogen bonds there. And it also has its amino acid on here, and the amino acid it has is methionine, and we'll see why later why that is.
Sorry, say that again.
Methionine. So AUG is the codon that binds with the anticodon of the tRNA. And then the large subunit binds. So then you get the large subunit. I should have drawn this further down, but I can't move it now. Nope. All right, so the large subunit's then going to bind up here. It's not going to be that large. Something like that. All right, so that's initiation. So messenger RNA has the code, the anticodon of the tRNA binds, the small subunit binds, then the large subunit binds. All right, now we're going to move on to then elongation. So I want to draw this further down. We have our mRNA, we have our small subunit, we have our tRNA with methionine on it. I'm going to draw the ribosomes in red. Small subunit here, large subunit here. And this is sitting in the P site. So in elongation, another tRNA binds at the A site. and it's going to have another amino acid. And now we need to elongate that chain of amino acids. So the peptide bond is catalyzed by the section called peptidyl transferase. And so now we get a peptide bond forming there. And now this tRNA in the P site is useless. It doesn't have an amino acid anymore. It needs to go find another one. And so in order to get rid of it, the ribosome needs to shift. And then that tRNA moves to the E site and then leaves. And so what we're left then with is now a tRNA with 2 amino acids on it. And as it's shifted over, that one with 2 on it now is in the P site. And then now the A site is open for another tRNA to go in and bring another amino acid. And this cycle will continue. And that chain will elongate.
What are the big bubbles called again?
Amino acids? Or ribosomes?
Yeah, those are ribosomes. Okay.
So it's the large and small subunit. All right, so this process will go continuously. And each time you go through, you add another amino acid to this chain. And so the chain keeps on getting longer and longer and longer. Okay, any questions? Yes?
So question, is the rRNA the big subunit?
Both of them. So large subunit and small subunit are both made of ribosomal RNA, which make up the ribosome.
Okay, so question for the EPA thing.
Mm-hmm.
Is it always the EPA?
Yeah, always in that order. But they go in the A site, move over to the P site, and then move out at the E site. So it's APE if you want to think of it in the right order. APE. Yes. Okay, any other questions? Okay, so we'll move on to the last then. Termination. You've got your mRNA. You have your large subunit. Your tRNA is in the P site here. And now it has all these amino acids hanging off of it. The small subunit is here. And so elongation goes continuously until you get to a stop codon. So a specific sequence which binds to what's called a release factor. And that basically just makes everything fall apart. Okay, so the mRNA, tRNA, the ribosome, and now our polypeptide break apart or dissociate. And go their separate ways. The ribosome can be reused, the tRNAs can be reused, and the polypeptide then goes to be folded into its final shape as a protein. Yes?
Can you, sorry, I was writing down, can you repeat just that last part, what happens after the dissociation?
They just all go their separate ways. The ribosome can be reused in another initiation site. The tRNAs go to recharge themselves, get another amino acid. The polypeptide is then available to be folded into a protein. And that's it. That's the process of translation. Okay. Any questions? Any more questions? Okay, so now we've completed the full process. Could you, if given a DNA sequence, then figure out what it codes for?
Yeah.
Maybe. All right, well, let's give it a shot. Okay. So here's a strand of DNA. Yes?
What's the sequence that makes it stop?
Oh, it's a few different kinds. So I'll actually put it in here. So this is one I just got off of the internet, which is a little bit, it's the same as the one in your book, only it looks different. Everything's the same. But there are 3 stop codons. UAA, UAG, and UGA. But there's only one start codon, and that's methionine. Oh, sorry, AUG, which also codes for methionine.
We need to
Hmm?
know those. Well, we need to know those.
No, so you'll always be given this table if asked to translate a messenger RNA sequence or a DNA sequence. Okay, so I'm going to go back. And now they're all stuck together. Okay, so get with, I'm going to give you guys a few minutes to figure out how to go. This is a DNA sequence. How do you take this DNA sequence and then figure out what amino acids are in the polypeptide? So go take it through the steps of transcription and translation and tell me what are the amino acids, what is the amino acid sequence? All right, so the first step you're going to do is transcription, right? So you're going to convert this to a corresponding RNA strand, right? So you just use your base pairing rules. All right, now what do you do? What's the second part? Okay, yeah, so here's the tricky part. You want to just do this, right? But that's not how translation works. You have to find a start codon first. So what you're going to do is go along here until you find the start codon, which is AUG. Okay? So if you would have started just at the beginning, you would have missed that AUG because it would have split up here and here. Right, but you actually don't start until you get to the AUG. And then after that, I would just split it up into these codons. And then you need your table. To figure out what the rest of them code for. So the first one, AUG, is start methionine. So I'm just going to do the abbreviations. All right, the next one is AAG. AAG, which is going to be lysine. And then CCC is going to be proline. And then GUG is going to be valine. UCA is serine. UGC is cysteine. And then UAA is stop. Okay? So I'm not going to do GGC and I'm not going to do UAA. UAA doesn't actually code for anything. I'm just going to stop there. And then this then is my amino acid sequence. So at this stop codon, rather than getting another amino acid, you're going to have a release factor bind there. And then that's going to make everything split apart. Okay? Got it figured out?
Where can we find this witchcraft table?
That's on the worksheet. So that's what we're going to do now.
So the